Politechnika Poznańska.
Building a rocket like this is a challenge. A lot of work, a lot of time, and a lot of sacrifices. Creating this rocket is months of hard work that is rewarded with opportunities to develop engineering and research skills. And of course that indescribable feeling at the moment when T-0 appears on the screen and the rocket lifts off. PUT Rocket Lab Student Research Group gives not only the chance to participate in interesting projects, but also educates new engineers, gives the opportunity to meet great people with similar interests, and above all, creates a safe space to learn engineering under the supervision of scientists. In fact, the goal is not the contest itself. The goal is to gain knowledge, experience, and develop passions. That's why we put a lot of emphasis on doing things in-house from scratch. It gives us a really great understanding of how all the systems and subsystems work. We're called PUT Rocket Lab, and we are going to present the results of our long journey. Hexa 2.
The purpose of our project is to create a single-stage hybrid rocket design for Spaceport America Cup 30,000 feet SRAD category. It all started establishing basic design assumptions. Rough estimates of parameters like vehicle mass, drag coefficient, and airframe diameters allowed us to assess required total impulse and thrust. This demonstrated the need to develop propellant and engine design tailored for those requirements. We started by developing a hybrid rocket engine for ground testing called BEM, Ballistic Evaluation Motor. Through an extensive test campaign, we developed an ablative heat protection system and the process of pressure-less gravitational fuel casting with controlled temperature profile. What's more, in order to gain some experience in the field, we created Level 2 high-power rocket, Hexa 1, which successfully paved the way for its successor. Parallel to the engine test campaign, we conducted CFD and flight dynamics analysis on aerodynamic loads. Obtained results narrowed down the range of design requirements and gave us some intuition about performance sensitive on different parameters.
Hexado Propulsion is a self-pressurized O-class hybrid engine that consists of a structural aluminum tank, oxidizer feed manifold with an electrically driven servo valve, and a compact combustor with a single-port fuel grain. We call it BS2, which stands from Broomstick 2. The engine was designed to match Hexa 2 flight dynamic requirements and to deliver 4 kN of lift-off thrust and a total impulse of around 34 kN/s. The tank is a cylindrical tube made from 6082 aluminum alloy welded with a bulkhead machined to a shape minimizing stress at weld location. The tank is normally capable of storing liquid propellants at a pressure of 60 bars, tested to a safety factor of 2. The tank is equipped with an oxidizer relief system, thanks to which we are able to control if our rocket is fully loaded, or we can reduce propellant temperature as well. BS2 engine oxidizer feed manifold consists of SRAD electrohydraulic servo valve and the expansion joint that reduces stresses in the feed system while the engine is working. The valve is controlled by HECU, which is responsible for controlling the position servos based on a programmed timing and events. Oxidizer Injector is an open-type swirl injector that creates a spray cone of liquid nitrous oxide injected into the pre-combustor. Such configuration creates intense recirculation flows, providing nitrous oxide evaporation and decomposition before flow enters the port. The design enhances combustion stability and C-star efficiency, especially for short combustors like the one used in BS2. The engine has a bell nozzle with a graphite convergent divergent throat insert to withstand high temperature of combustion products and a phenolic divergent expansion section matching the design area ratio.
For our engine size, popular polymeric fuels like pure polyethylene or HTPB turn out to have too low regression rate. Using these materials as fuel would require either a very long combustion chamber or result in extremely lean combustion. A campaign of more than 20 hot fire tests on a scaled-down engine lead us to the final composition. The fuel is based on microcrystalline wax and polyethylene. We also developed the technology for fuel manufacturing. The fuel is obtained in the process of pressureless gravitational casting and then is slowly solidified in the thermostatic chamber.
While the oxidizer tank is also a structural element of the rocket and acts as an airframe, the rest of the fuselage elements are both carbon and glass fiber tubes with honeycomb cores. All composite structures except for fins are manufactured by us using hand lamination techniques. As we mentioned before, we performed a series of CFD analyses to predict the rocket performance during the flight, as well as to estimate the aerodynamic loads acting on the vehicle. The obtained aerodynamic characteristics of our rocket served as an input to an in-house developed flight trajectory simulator. The need for developing such a tool arose from the lack of an open license software to which we could import obtained aerodynamic data. To address the risk of thin aeroelastic flutter, we have used the data published in an often used NACA technical note 4197. Because our fins are made from carbon fiber composite, we had to use published data to design the fins as aluminum and then rescale their thickness to provide required torsional stiffness. The scaling factor was established in a set of experiments performed on a purpose-built torsion pendulum, which is an indirect but simple and cost-effective way. Installation of the 2020 SA Cup gave us time to redesign the recovery system. Starting from the bottom, there is an aluminum coupler to which both main and drag chutes are attached. The proper design of the coupler is critical. In order for the coupler to be light and durable, we performed a thorough study including multiple finite element analyses from which we obtained the final design. Besides the eye bolt to which the main chute is attached, two redundant main chute release mechanisms are also mounted on the U section of the coupler. When the rocket approaches the apogee, two E-matches are set off, causing the black powder to combust, and the piston-like mechanism pushes the drag chute, which then acts against the nose cone, causing it to jettison. The drag chute deploys and the rapid descent phase begins. When the altitude in the descending phase reaches 500 meters, two E-matches are triggered by the avionics, causing steel pins to eject, which eventually causes the release of the drag chute. It is worth mentioning that the release mechanism is designed in a way that it does not matter which of the pin ejects, the drag will be released. The drag chute pulls the main chute out of the fuselage and the main deploys. The parachutes were in-house designed. We developed an automatic design tool which incorporates gradient-based optimizers and genetic algorithms. This software allowed us to explore the design space as well as create optimal design in terms of trade-off between canopy mass and its strength. The drag chute was designed as a normal single canopy parachute with the diameter of 1050 mm, while the main was designed as a disc gap band with the diameter of 3250 mm. In order to check whether the developed tool provides us with a shape of canopy, which has previously assumed drag and pressure coefficients, a series of 3D CFD analyses were performed.
As you can see, right recovery activation timing are crucial for a safe mission. Reliable flight computer is very important, so it is the most polished part of the avionics subsystem. Bare minimum is flight computer with the main goal of firing prior charges for the recovery purposes. It is also responsible for register the whole flight. Apogee detection algorithm is based on rocket position, derived from the inertial measurement unit and pressure sensor measurements. Moreover, for safety, the main microcontroller is brownout protected and pyro channels contain continuity checks. This solution is one of the finest achievements of cooperation of IT and electronic development teams members. For redundancy purposes, commercial solution Ultimax G3 is used. Besides bare minimum, our avionics subsystem contains telemetry, tracking, and oxidizer tanking control solutions.
Telemetry board is a data acquisition and communication module. It gathers data from other modules for processing it by our development compressing algorithms to maximize telemetry performance. This data is used later for post-processing purposes. Telemetry board and bare minimum were tested several times with our previous rocket, Salami.
Companion board is a Raspberry Pi Shield. It gets oxidizer pressure and battery condition. It also gathers onboard data via Wi-Fi. Noc board is an ESP8266 microcontroller board. Its main purpose is to get dynamic pressure via pitted static tube. We're especially proud of our GPS trackers as they have been well tested in many flights. The data from the trackers then is sent back to the receivers. The receiver was designed as a developmental LoRa gateway that can distribute data by the most popular wired and wireless protocols. The device is assembled with a dual-core microcontroller with integrated Bluetooth and Wi-Fi modules, ESP32.
All of the avionics subsystem components are located on the top of the motor mount in the composite epoxy-based fiberglass tube. Utilization of light materials like reinforced plywood and 3D printed PLA parts allow to keep assembly mass below 3 pounds. What's more, we have developed our own ground operations system. PCC is Hexa to Mission Portable Command Center. It allows data acquisition from telemetry link and also its visualization. And of course, it helps us with remote oxidizer tanking. It's connected with executive system launchpad box located near our launch rail.
In order to ensure the flight of our rocket, we have created a launcher dedicated for Hexa 2. The launcher has launch rail with a total length of about 9 meters and allows us to easily install the rocket with the help of winch and launch it at the right angle. An integral part of the launcher is the refueling system, which allows us to remotely refuel the rocket. Hexa 2, after leaving the launcher, flies to an altitude about 30,000 feet and then at the apogee deploys the drag chute and descends at the constant speed. At an altitude of 500 meters, the rocket deploys the main parachute so that it descends to the ground at 7 meters per second.
Rocket engineering is considered difficult for a reason. Designing rocket is quite a big deal. And of course that's why we do it. If things are going too easy, it means we are far from optimum. Calculation, testing, drawing conclusion, over and over again. There were difficult moments, but we fueled ourselves with positive energy to make this project come true. We did it. This is Hexa 2.
When we started this project, many said that it's a mistake to aim at the most difficult category from the beginning. And they were right. That ambition backfired on us many times, causing setbacks and countless efforts to make things work. The approach of chasing the optimum gives no place for error. And there were times when we really thought that it's a dead end. But thanks to hard work, exceptional dedication and great cooperation between people of many different backgrounds, the rocket is here. And we are all enriched by knowledge, experience and personality traits that couldn't be gained in any other way.